Chapter 2.3, Functions. It turns out the vast majority of equations are naturally occurring functions. Therefore, we become very interested in exactly what it means to be a function and what are the parameters of a function. So today, we're going to look at functions. A function is a relationship between two sets where every element of the first set, and here's what makes it a function, corresponds to exactly one element in the second set. Domain, or what we call the elements in the first set, for our purposes, it's going to be x, right? We're going to have x's and y's, but specifically the elements in the first set. And the range, or what we call the elements in the second set, for our purposes, y. So domain, x, range, y. So when you're asked about the domain, you're always thinking, oh, x's. What is it possible for x to be or not to be? Okay, so to determine if something is a function, if you're looking at just a set of coordinates, look at the x value. As long as the x's are all different, it will be a function. If there are x values that are the same, check to see if they go to different y values. If they do, it is not a function. For example, here's a list of coordinates, and the question is it a function? Well, the x's are 9, 6, -1, and 7. It is a function. Doesn't matter what the y's are, right? Only that every x, every element in the domain, goes to one y. Okay, so this one is a function. This one, is it a function? Well, let's check the x values. 3, -5, 3. Wait a minute. Do those 3's go to different y coordinates? And yes, they do. This is not a function. Also take note that we could be given this exact same question just in a different format. Something like this. Oh, definitely is a function. All my x's are different, right? Or if we have something like this, some kind of mapping, it's telling me the exact information, right? Oh, this is the 0.21, 32, 35. Whoa, wait a minute. I've got something in the first set here in my domain going to different values in the second set, not a function. If we're looking at a graph, we have something called the vertical line test. So let me put a few graphs up here. Bear with my drawings, of course. Okay, to determine if these are functions, I use the vertical line test, which means if there's anywhere on the graph that I can draw a vertical line and it crosses it more than one time, like this one, it's not a function. If a vertical line crosses your graph more than one time, it is not a function. If the vertical line can only cross the graph and one point, it is a function. So is this last one over here a function or not? Well, it is not a function because it does not pass the vertical line test. Notice this is telling us the same thing. It's just I have to think about it differently when it's in a different format. For example, what this is saying is perhaps when x is 1, I have a value of y that's positive 2 and a value of y that's negative 2. So 1x is going to 2 different y's. That's exactly what this is saying. 1x is going to 2 different y's. If I were to list these as coordinates, -1, 2, -1, -2. And every one of these x values goes to 1y. 1x goes to 1y. 1x goes to 1y. So all of my x's are different. Okay? We could also be given an equation and asked to determine if it's a function. If we're looking at the equation, we're going to look at the y value. If it has an even exponent, absolute value bars, or anything that makes a positive and negative y correspond to different x values, then it is not a function correspond to the same x value, then it is not a function. So all I have to do to determine if these are functions or not, or look at the y's. Okay, so this is a function. This is a function. Okay, oops, this one is not a function, and this one is not a function. Again, this is telling me the same information. It's just I have to think about it differently if it's in a different format. Because what this is saying is, for one example, if x is 5 or -5, I'm sorry, if y is 5 or -5, those both correspond to 0, right? So I would have the coordinate 0, 5, and 0, -5, which would be a solution to this problem. It doesn't matter if the x's are the same, remember? So over here, if x is 5, it goes to 0, and if x is -5, it goes to 0, but think about what those coordinates look like. Those do not have the same x value, so it's automatically is a function. Over here, I can find 2 points that have the same x but different y's, so it's not a function. Likewise, if I think about what these graphs look like, and right now I may not know what they all look like, but eventually I will. I should know this is a line, right? So that's the graph of a linear equation or a line. So it passes the vertical line test. If we don't know already, we soon will, that this is the parabola. So it passes the vertical line test. This one with the y squared has this shape, which does not pass the vertical line test. And we should know this is a circle, which again does not pass the vertical line test. So they're all telling us the same information. I just think about it in different ways. So to recap one more time, if you're looking at a list of coordinates, look at the x values. As long as they're different, it's a function. If any of them are the same, then look to see if they go to different y's. If they do, it's not a function. If I'm looking at the graph, do the vertical line test. As long as it only crosses the function one time, or the line one time, it is a function. If it crosses the function, or not, it wouldn't be a function. If it crosses the graph at more than one point, when you draw a vertical line through it, it's not a function. If you're looking at an equation, look only at the y's. As long as the y value doesn't have an even exponent or absolute value bars or anything that makes the y value the same for a positive or a negative, then it's not a function. Okay, so now that we can determine if something is or is not a function, then we need to be able to find the domain and the range of a function. Remember, the domain means we're asking about the values of x, and the range means we're asking about the values of y. If I have determined that something is a function, I want to solve it for y. Don't forget this step. It could cause you to make a mistake. So up here, since we know this one is a function, I'm going to solve it for y before I can even answer the question about finding the domain. Same thing here. If it's not a function, don't worry. We'll talk about those when we discuss range. It'll be a very similar concept. Okay, so first of all, solve it for y. Now, the domain of a function is all real numbers, except in two possible situations. Technically three, but that'll come way later. Two possible situations. And that is if I have a denominator with an x in it or a radical with an x under it. Denominators cannot be zero, so that gives us a problem. And you can't take an even root of a negative number if you want to stay in the real number system. So that's another problem. So to find the domain of a rational function, set the denominator equal to 0. Denominators cannot be 0. So whatever value or values make the denominator 0 must be removed from the domain. You cannot let x be a value that would make a denominator 0 when you plug in for it. To find the domain of a radical function, set whatever is underneath the radical to be greater than or equal to 0, because you don't want what is underneath the radical to be negative. To find the domain of an equation that is not a function, we're going to follow the rule for finding the range. All right. To find the range of a function, it requires some thinking. We need to know if it is possible for the y value to be negative, 0, or positive. So we will consider each situation. Okay, we really do that with the domain also. It's just very easy to isolate which functions give us problems with zeros and negatives. Denominators can't be 0. Negatives can't be under radicals if we're going to stay in the real number system. All right, so let's apply this idea. All right, so first of all, let's determine which ones of these equations are functions. All I have to do is look at the y. So yes, it's a function. Yes, it's a function. Yes, it's a function. No, it's not a function. Yes, it's a function. Yes, it's a function. If it is a function, then, and I'm asked what the domain and range is, the first thing I want to do is solve it for y. So solve for y, solve for y. Wait, let's solve this thing for y. So what I'm considering when I'm trying to find the domain is really the function in this form. Not a function, so we'll deal with that separately. Solve for y, solve for y. Okay, if it's a function, the domain is all real numbers unless there's a variable in the denominator or under a radical or in the argument of a logarithm, but we won't have those for a while. Okay, so, this is all real numbers, right? The domain is automatically all real numbers unless there's a variable under a radical or in a denominator. I could also think about the shape of this graph and realize my domain is all real numbers. Okay. What about the ones then where I do have an issue with my domain? Let's do the ones with the denominator first. If there's a variable in the denominator, that denominator cannot equal 0. This one only has an x in the denominator, so it means x cannot equal 0. That is my domain. So the way I would write that in my interval notation is negative infinity to 0. Use the parenthesis to indicate I don't want to include the 0. And then or 0 to infinity. So in other words, this is the domain for, the interval from negative infinity to infinity, except it doesn't have the 0. Everything except the 0's been taken out. Here's another one with a denominator. So that denominator cannot be 0. It's not that x can't be 0, right? The denominator can't be 0. So on this one, if we add 3 to both sides, x cannot be 3. That's my domain. X cannot be 3. Okay, again, negative infinity to 3, but don't include the 3, or 3 to infinity without including the 3. For a radical, I'm thinking, well, I can't take the square root of a negative number, so I want whatever is underneath the square root to be not negative. Mathematically, that's saying greater than or equal to 0, right? Everything that's greater than or equal to 0 is not negative. So I can solve this little inequality for x, and it's telling me my domain. The domain is x is greater than or equal to negative 1/4. So I'm going to use a bracket because it can be 0. I can take the square root of 0. That's 0. But I can't take the square root of a negative number. All right, same idea over here. Has to be, whatever's underneath the radical has to be greater than or equal to 0. Well, that's already solved for x. So x is greater than or equal to 0. Must be, what am I doing? X is greater than or equal to 0. Must be my domain. So to write it in interval notation, I want to say from 0 to infinity, including 0. Remember, those infinities always get parentheses. Okay, now let's talk about the range. The range, I'm just going to kind of think about, is it possible for my y, my range is asking about y values, to be positive, negative, or 0? That's what I was concerned about in my domain also. So I'm just going to ask myself, for example, on this one, is it possible that I could plug in a number into x that would make this equal a negative number? Sure, if x is 0, y is negative 5. It's possible for y's to be negative, yep. Could it be positive? Yeah, if x is, let's say, 10, 20 minus 5 is a positive number, that's fine. Can it be 0? Could I solve this where y is 0? And some people don't quite see that that's the case, but I can make a little equation and see, do I get a value? Oh yeah, if x is 5/2, then that's 0. So y could be positive, negative, or 0. Again, I could look at the graph. We'll talk about that in just a second. So the range for this one is also negative infinity to infinity. This one, however, remember, when we take the square root of a number, if the square root starts out in the problem, it's considered the principal root, or only positive. So there's no way y can be negative. If I take the square root of 16, it's positive 4. So far I've got to toss out the negatives. Oh, I can take the square root of 0 as 0, so 0 is okay, and of course positive numbers are okay. So the range for this is 0 to infinity. okay? Because you can't take the square root of a number and get a negative value. So no negatives can be included in the range. Okay, this one I'm asking myself again, is there a number I can plug into this x that'll make this entire fraction, or in other words, the y, negative? Sure, any negative number. So negatives are in. Positives are in because any positive number you put down here. But is 0 in? To make a fraction equal 0, it means the numerator must be 0. And in this case, I can't change that numerator to a 0. It's a 2. There's no variable, right? Nothing changes. I can't make this fraction in this form equal 0. So my range in this one is the same as the domain. It can be, that fraction can be negative, it can be positive, but it's impossible for it to equal 0. If I had a fraction like this, then the range is all real numbers. The domain is still x cannot equal 0 because I can't have a denominator 0. But in this case, I could make the numerator 0 by plugging in a -2 for x. So it's not just all fractions have this range. I just want to think through that process. Okay, so this one is the exact same thought process as this one. I already know that the negatives have to be kicked out of the range because square roots, even roots, equal always the principal root if it starts out in the problem. I can take the square root of 0, which is 0, so 0 is included. And of course, the square root is always considered positive. So the range is 0 to infinity. And this one gets the same thought process as this one. The numerator could very well be negative, so the fraction is negative. The denominator could very well be negative, so the fraction is negative. The denominator could very well be positive, so the fraction is positive. But I could not make this fraction equal to 0 because I just have a constant in the numerator. For a fraction to be 0, the numerator must be 0. And since there's no variable up there for me to vary to 0, it can't be 0. Okay, on this one, we're going to think about the domain and the range the same way. And the question then becomes, if I'm trying to figure out the domain, is it possible to plug numbers in here to make x positive, negative, and 0? Since this is raised to the 6th power, no matter what value I plug in here, positive, negative, or 0, that'll never be negative. Negative 1 to the 6th power is positive 1. This can never be negative. My domain, my x values, can't be negative, so negatives are out. I can raise 0 to the 6th power to get a 0, and then any positive number raised to the 6th power is positive. So the domain for this one is 0 to infinity. And then the range, I'm thinking, well, is there any number that positive, negative, or 0 that I cannot raise to the 6th power? The answer to that is no. I can take -2 to the 6th power and evaluate it, 0 to the 6th power, 5 to the 6th power. So my range is all real numbers. Okay, let's look at the domain and range on some graphs. Right, so I don't have any drawn on here. I'm just going to go back and draw a couple of graphs for us to have this conversation with. Oh, let's imagine that this ellipse goes through this point here. That's what I was trying to draw. Okay, to determine the domain and range from looking at a graph, again, I've got to think about, well, the domain is talking about the x values. So I'm going to just imagine if I go from left to right, where is the graph, where's the graph, where's the graph, where's the graph, where's the graph? And graph starts right here, right? And then there's a piece of graph all the way to here. So my x values, my domain, go between -4 and +2. So the domain for this function, this is not a function, the domain for this relation, right, is from -4 to +2. And I'm going to do the same thing with the range, except I'm thinking about my y values. So I'm going up my y-axis. And I realize there is no graph anywhere until I get to where y is -1. And then there's graph for every y value all the way up to +1. So my range is -1 to +1. On this one, my domain, my x values, if I think about going in this direction, there's no graph, no graph, no graph until I get to when x is -2. And as I follow it, the last thing I see on this graph is an arrow. Arrows indicate that's going forever. It's not only going up forever, it's going right forever also. So the domain for this one is -2 to infinity. The range means I'm going up my y-axis. So as I go up my y-axis, the first thing I get to is an arrow, which is going not only right, but down forever. And the last thing is another arrow going up forever. So my range on this one is -infinity to infinity. Domain is asking about the x's. Well, I have arrows going in both directions. So my domain is -infinity to infinity. And the range is asking about the y's. And the first thing I come to when going up my y-axis is an arrow that's going down forever. The last thing is an arrow going up forever. So the range is -infinity to infinity. Okay, so last one. What's the domain and range for this one? Domain, arrow first. It's not only going up forever, it's going to the left forever. And the last thing I see is another arrow. Range is asking about y's. So if I go up, the first thing I come to is where y is -1. And the last thing are arrows. Okay, now that we know what constitute a function, we can use function notation. So this is our function notation, f of x. Anytime you see f of x, you can replace it with y. And if the equation you have is a function with the variables x and y, then you can replace the y with f of x. You cannot replace a y with f of x arbitrarily. but if you determine it's a function, then you may. But anytime you see f of x, you can replace it with y. Okay, this f of x is just a shorthand notation. Instead of saying evaluate the function when x is 3, I can simply say find f of 3. F of 3 means take the function f, right, and replace every x value with a 3. So negative 3, but instead of times x, times 3 plus 4. So f of 3 equals negative 9 plus 4 equals negative 5. So f of 3 equals negative 5. Also, if I'm given something in this format, it tells me a lot of information. I know my x value is 3, and because f of x is y, then I know y is negative 5, right? So I know here that x is 3 and y is negative 5. So I could say find g of 2. Let's find g of negative 2, just so that we have this conversation again about negatives. That means I'm going to take the function g, and everywhere there's an x, I'm going to replace it with negative 2. Now be careful, this negative has nothing to do with this exponent. If it did, it would be inside parentheses like this, right? So that's negative 2 all squared, plus 4 times negative 2. Everywhere there's an x, replace it with negative 2 plus 1. So this negative stays negative, but now I've got a negative 2 times negative 2, which is positive 4. 4 times negative 2, positive 1. So negative 12 plus 1, negative 11. G of negative 2 is negative 11, meaning when x is negative 2, y is negative 11. We can also evaluate things like expressions inside our functions. Like I can say find f of a, which simply means change every x to an a instead of a 3 or a negative 2. So f of a is negative 3a plus 4. I could say find g of x plus h, which would mean everywhere there's an x, replace it with x plus h. G of x plus h is negative x plus h squared instead of x squared plus 4 times x plus h plus 1. Okay, and then do our algebra. Negative, I hope we remember how to multiply this out. Square the first one. Multiply everything together, so x times h and double it. And square the last one. Distribute that 4. And then finally also distribute that negative. Negative x squared minus 2xh minus h plus 4x plus 4h plus 1. So functions. Determining if something is a function, whether I'm looking at a list of points, a graph, or an equation. Finding the domain and range of these functions and relations. And then function notation. Let me know if you have any questions.